Our situation was that we had variables over here, horizontal misdistance and vertical misdistance, where we had assumptions about their probability distributions. But we were interested in the probability densities distributions of other variables, namely the radial misdistance and the angle of the miss. We went through how, in general, do you find the CDF and the PDF of a variable that is a function of two other random variables. And we said, this is the way to do it. You find the CDF by taking this integral, which is the joint PDF of these two variables over the region where your condition is true. And then you take the derivative of that guy to find the PDF. And in our case, this joint PDF was this guy, which looks like this. So we need to integrate over the proper region in the XY plane down here to find the volume under this surface. So now let's get to our situation. Here's for radial misdistance. Look at probability distribution. Cumulative distribution from PDF. Here's the condition. Region of integration where this is true is a disk of radius r in the xy plane. It's where x squared plus y squared is less than or equal to r squared. Here's the joint PDF. Here's the region we integrate over. For the angle, it's the same joint PDF. It's everything inside the integral is the same, but a different region of integration. For this guy, it's a sliver of angle going out to infinite radius. So those look like kind of tough integrals to take. But because of the assumptions we made, converting to polar coordinates makes it rather convenient. And that turns out because we assumed equal variances of the x and y, the horizontal and vertical, and statistical independence. So that this little joint PDF, any slice through a level of constant likelihood is a circle. So it's fairly convenient to take the integrals in the polar coordinates. And when you convert to polar coordinates, don't forget to throw this extra r into the differential. So here was our joint PDF converted to our new variables, which are r and theta. There's no theta in it. Here's the extra r because of polar coordinates. And here's the region of integration of the double integral. Now that we know we're integrating over a disk of radius r. R goes from 0 to r. Theta goes all the way around 2 pi. Now we're just taking an integral, and we can do that. Pull out the 1 over 2 pi. This double integral splits up into a product of the individual variables. There's no theta in here other than d theta itself. You have this left with r. I won't go through this in detail, but this is in the form of e to the minus u du. You make these substitutions. That's an easy integral to take. Turns out to be this. So now we've got the CDF of the misdistance. The PDF, you take the derivative. I'm not going to go through that. It's easy enough. Here's what you get. Lo and behold, that is the Rayleigh distribution. It's derived some sort of foundation for the Rayleigh distribution, where it might have come from. Here's the CDF, here's the PDF. Here's what the PDF looks like for multiple values of that sigma. That sigma, remember, was the standard deviation of the horizontal and vertical errors. It's not the standard deviation of the Rayleigh. The angular error is easy enough. Same thing inside the integral, but now the area or the region of integration is that sliver of angle. So R goes all the way out to infinity. The angle goes from 0 to our argument, our angle argument. That becomes this. This integrand is just the Rayleigh itself. So when you integrate it over all R, you get 1. So that's easy to take. And you end up with a uniform distribution for angle. So any angle is just as likely as any other angle. The angle is uniformly distributed. Here, this sort of could be sample dart throws. The green would be dart thrower with a smaller sigma than the red thrower. It has a larger sigma. So those are the basic distributions. There's the Rayleigh. Here's the, well, uniform. So next we'll get into other things to explore about the Rayleigh distribution.